This
and produce
conference will now be
more
recorded.
man-made carbon dioxide. As this CO2 dissolves in seawater, it reacts with the water molecules to form a compound known as carbonic acid. Through a number of other subsequent chemical reactions, this formation of carbonic acid and dissociation in seawater then leads to additional changes in the water chemistry, including things like a decrease in pH or an increase in acidification, as well as a decrease in the calcium carbonate saturation state, which define the term of ocean acidification. The saturation state is the one that people are most likely less familiar with in these two processes, and it's indicated often by an omega symbol. And it essentially tells us about the relative stability of calcium carbonate minerals in seawater. When values are less than 1, the waters are considered what we call undersaturated with respect to calcium carbonate, and dissolution of calcium carbonate structures is thermodynamically favored. When values are greater than 1, water is considered supersaturated with respect to calcium carbonate, and formation of calcium carbonate minerals tends to be favored. Calcifying organisms in the ocean create their skeletons and hard parts from calcium carbonate minerals, and therefore changes in the saturation state and pH driven by ocean acidification can influence or affect their ability to calcify and create their hard skeletal structures. These calcifying ecosystems are critical to the health of both marine and coastal ecosystems. They include organisms such as coral as well as oysters that support not only our economy, but also many factors of human health. They can provide income and sustenance in the form of food. They can also provide a source of revenue through tourism, as well as other ecosystem services such as coastal protection. They often play important roles in cultural values and can be a source of investigation for new materials that are used, for instance, in the formation or development of medical treatments. So as you can see, they provide a significant number of services to our communities as a whole, and thus understanding the potential threats or factors that may influence their overall health is a really important field of study. While open ocean acidification is driven primarily by the increase in anthropogenic carbon dioxide, coastal environments are affected by a number of additional factors that can further exacerbate or increase the acidification in coastal environments. These can include things like increased nutrient inputs, changes in the stream or river water input, extreme or excessive flooding and runoff as a result of storms, as well as upwelling from the deep ocean. The figure on the right-hand side here indicates graphically many of these processes that can influence the acidification in coastal environments, and we often refer to these collection of processes as coastal acidification. In addition to more long-term changes such as nutrient pollution or upwelling, there have been previous studies that have shown runoff, specifically from tropical cyclones or high rainfall storms, can cause stochastic or unpredictable coastal acidification events in these environments. In addition, or in the background or on top of long-term changes, these point or short-term events can have significant impacts on the overall ecosystem health, especially under chronic exposure to these low or high acidification environments. Across the United States, there are many regions on the Gulf and East Coast that are extremely prone to hurricane activity. In particular, many states on the Gulf Coast, such as Texas, Louisiana, and Florida, are often hit by several hurricanes in a given time period. The graph or the graphic feature on the right-hand side shows the hurricane landfalls that have been recorded from 1850 through 2020, with the gray colors indicating less than 10 hurricanes recorded and the dark blue indicating more than 50. And we can see, particularly in the Gulf and southeastern US, many of these regions experience high hurricane activity. In addition to being commonly affected or more affected by hurricane systems, many of these regions, or in the coastal environments, are home to valuable calcifying ecosystems, including oyster reefs indicated along the coastlines by the yellow symbols, as well as coral reefs indicated in the Gulf Coast off the coast of Texas and Florida, shown by the red coral symbols. Given the prevalence of hurricanes and also the presence of calcifying reefs, tropical cyclone-induced acidification may pose a significant threat to these ecosystems. So it's important to understand and know how these storms may impact the coastal acidification levels. For the majority of this talk, we're going to utilize a single storm as a case study for a very high rainfall tropical cyclone event and the potential impacts it has on the calcifying ecosystem. Galveston Bay, which is our study site for this project, is one of the largest estuaries on the Texas coast and is composed of 3 primary regions. The center of the bay is often referred to as Galveston Bay. The upper northeast corner is often referred to as Trinity Bay, and this arm on the eastern side is often referred to as East Bay. The bay sits southwest of the Houston metropolitan area and in the southeastern side of the Texas coast. Entering the bay are 2 major freshwater sources, mainly the Trinity River, which is the primary freshwater source to the bay, drains the Dallas-Fort Worth area, whereas the Houston Shipping Channel provides the major drainage point for the Houston metropolitan city. In addition to incoming freshwater, the bay receives incoming seawater from the Gulf of Mexico through the area on the bottom right-hand corner, known as Boulevard Roads. This is the primary location of tidal exchange, and about 80% of this occurs through this narrow inlet channel. Throughout the bay, we also have a relatively high range of residence times, anywhere from 0 days, shown in blue, to more than 45 days, shown in the dark red colors. And these residence times not only vary spatially, but also seasonally across the year. But we can see for the most part, the longer residence times, upwards of 30 to 45 days, tends to occur in the upper regions of the bay, farthest removed from the mouth of the bay and the Gulf of Mexico seawater. These include areas like Upper East Bay, as well as Upper Trinity Bay here in the right-hand corner. Galveston Bay itself is a very critical estuary ecosystem for not only Texas, but also the national economy. It is a major shipping port, including 3 major shipping destinations, as well as a significant amount of the petrochemical production for the entirety of the US. In addition, it's home to very valuable oyster reefs that are a critical ecosystem that support the bay. These not only provide income and are a fishery resource themselves, but also create critical habitat for many other fishery species in the bay. They act as a source of natural water filtration, helping to keep the ecosystem healthy. They also stabilize the shoreline and protect the shoreline from erosion and storms. So we can see they provide a number of significant services, not only for our bay or for this specific ecosystem, but also on a national scale. So why do we care about the carbonate chemistry? Like I mentioned earlier, oysters are considered a calcium carbonate species, or a calcifying organism. They create their shells from calcium carbonate. However, they're a unique organism because at different stages in their life cycle, they actually create different forms of calcium carbonate. Larval or baby oysters create their shells from what's known as aragonite, which is a more soluble form than the calcium carbonate created by adult oysters for their shells, which is known as calcite. The right-hand figure shows the growth of a larval oyster in the first couple of days of calcification under supersaturated conditions on the left-hand side, when saturation state is greater than 1, and undersaturated conditions on the right-hand side, when that saturation state is less than 1. So what we can see is that particularly in undersaturated waters, we lose the uniform round shape of the shell, starts to become distorted, and these green arrows on the images indicate areas or features that may be indicative of the start or beginnings of dissolution. Thus, the saturation state in particular, as we mentioned previously, of calcium carbonate influences their relative ability to calcify and can also enhance dissolution of their shell structures. However, negative impacts of decreased saturation state are not restricted only to undersaturated waters. There have been laboratory and other field studies that have shown that larval calcification and growth impairment has starts to occur anywhere from saturation states of 1.9 or lower. So the water does not need to actually be undersaturated in order for there to be negatively observed effects, which can have significant impacts on ecosystem level chemistry when we're studying these changes. Long-term studies also provide a very important understanding of how the chemistry within these estuarine ecosystems is changing over time and what this might mean for some of these shorter term events. For instance, TCEQ, or Texas Center for Environmental Quality, has provided significant amounts of total alkalinity, or TA, as well as pH data that have been analyzed for the past 5 decades. This study indicated that we are seeing long-term decreases in both TA, which indicates the buffering capacity or ability of water to resist changes in pH, as well as pH in Texas bays, indicating an increasing trend of acidification over time. Given that the current or the base rate of acidification levels in an estuary ecosystem can also influence a response to a short-term event like a tropical cyclone, it's important to continue studying these ecosystems as they start to change and the carbonate chemistry starts to reflect large-scale global changes in ocean acidification and coastal processes. So now that we've started on the background of the Galveston system, I want to move a little bit into the background of what Hurricane Harvey was and why it was such a unique storm. Hurricane Harvey made landfall on the Texas coast as a Category 4 hurricane and has now been marked the wettest tropical cyclone in U.S. history. One of the reasons that it had such high rainfall amounts and volumes is because the storm actually stalled over the state of Texas between August 25th and 29th for multiple days, dumping large amounts of rainfall with some areas receiving more than 50 inches. The right-hand side is a map showing the Harvey rainfall rates or amounts after its major landfall and stall, where light green colors indicate little to no rain and the purple and black colors indicate areas that received excessive amounts or more than 30 inches of rain. And what you can see is that a majority of this rain is actually centered around this Galveston Bay region that I've highlighted in red. A large portion of the rain that not only fell on the bay itself, but also in the surrounding regions, drained directly into the bay ecosystem, and the runoff that drained into Galveston Bay was equivalent to 5 to 7 times the entire volume of the bay. So a significant amount of fresh water that entered the ecosystem and essentially caused a large-scale flushing event. This input of significant amounts of fresh water is reflected as well in the bay salinity. So here we have a plot of salinity on the y-axis along with a date along the x-axis beginning June 2017 before the landfall of Hurricane Harvey and ending in January 2018. The salinity values are pulled from buoys in the bay that represent different regions, where the blue corresponds to the blue dot shown in the center of the bay on the right-hand figure, and the yellow and red correspond to buoy stations near the freshwater sources and upper bay, including the Houston Ship Channel, shown in yellow, and in the Trinity Bay region, shown in red. Hurricane Harvey is marked now on this plot by the strong black line. We can see that prior to the landfall of the hurricane, middle of the bay, salinity tended to range between 15 and 20, while the salinity near the freshwater sources was lower, ranging from about 8 to 10. However, if we zoom in on the area just after Harvey, we saw a dramatic decline in the salinity at all points in the bay. According to all 3 of these buoy sites, each region became entirely fresh after Harvey for about a week, and these freshwater conditions extended anywhere from 5 days to 2 weeks, with recovery starting after that. However, very low conditions still persisted for many days after the storm. One of the impacts that this prolonged low salinity had was actually an oyster mortality event. The left-hand side indicates oyster mortality percentages based on sampling conducted by Texas Parks and Wildlife in October following the tropical cyclone. We can see that percentages of mortality ranged anywhere from 8 to 50 to 60% in the center of the bay to upwards of 95 to 100% in areas like the back East Bay, And these mortality events were driven primarily by prolonged low salinity conditions that was indicated by the presence of still clean shells in the bay with simply dead oysters, as opposed to significant burial caused by storm surge in other storms. The carbonate chemistry of this bay following the major tropical cyclone event is thus a critical component in order for larval growth and calcification to be supported and for this to help essentially allow these reefs to recover following this major traumatic mortality event. To investigate how the carbonate system responded to these major changes in freshwater influence from Hurricane Harvey, we conducted quarterly sampling that began in June 2017 before the landfall of Hurricane Harvey and extended through September 2018, 1 year after the storm event. In September 2017 as well, we had two separate sampling time points, both 2 weeks and 3 weeks after the storm, which helps us to inform or start to investigate potentially recovery timelines following this major event. We collected water chemistry samples for both total alkalinity that I mentioned previously, which indicates the relative buffering capacity or ability of the water to resist changes in pH, as well as samples for dissolved inorganic carbon. In addition to these, we conducted or collected concurrent samples for salinity, temperature, and nutrient levels. Utilizing all of these parameters together, we can then calculate the rest of the carbonate system, including pH and saturation state, to investigate additional changes in the bay water chemistry after Hurricane Harvey. The first thing that I want to look at is the response for fresh water in the ecosystem. So this is a plot showing total alkalinity, or TA, on the y-axis against salinity on the x-axis. The blue circles indicate discrete samples collected across the bay at those sampling stations for June 2017 prior to Hurricane Harvey. By fitting a regression line for our TA salinity relationship, we can estimate or extend and determine the approximate freshwater end member carbonate chemistry signal. This freshwater end member that we're estimating here is a combination, however, of all of the major contributing freshwater sources to the bay and not indicative of a single river end member. So more like a combined total end member for the system itself. In June, we see a relatively high freshwater end member based on this extrapolation, centered at around 1850 micromoles per kilogram. However, following Hurricane Harvey in September, we see a dramatic decrease in that freshwater end member at both of our sampling time points. Our sampling time point 2 weeks after Hurricane Harvey is indicated by the red-filled stars, with the freshwater end member close to around 850 micromoles per kilogram. And by the next week after, 3 weeks after the storm, indicated by the asterisk symbols, we are starting to see somewhat of a slight recovery with freshwater end member values closer to around 1300. By November 2017, about 2 months after the storm, shown by the yellow triangles here, that freshwater end member is still lower than Harvey, but currently higher than the freshwater end members calculated for both the September sampling time points, indicating potentially a continued recovery, and/or this may have been a result of seasonal influences and potentially recovered to more normal conditions. 2018 sampling points indicated here by the open symbols with purple squares for March, blue circles for June, and red stars for September, and the dashed lines show that our freshwater end member is very similar to those pre-Harvey conditions from June 2017, indicated by that solid blue line, suggesting recovery of the system by this sampling time point about 6 months after the storm. The reason why we saw such a dramatic shift in that end member value is likely due to the end member contributors. So under normal conditions, Galveston Bay can be considered to have 2 primary end members: Gulf of Mexico seawater, shown in blue, which enters through that channel of boulevard roads, as well as incoming river water from the Galveston watershed region, indicated by the brown arrows here. However, after Hurricane Harvey, we add the addition or increase the addition of a 3rd end member, and this is what we're going to call rainwater or runoff. These three end members have distinct carbonate chemistry signals that allow us to quantify or apply mixing calculations for the different end members. Rainwater has almost no alkalinity and very low DIC given the lack of rock weathering reactions that often give high alkalinity values to our river systems. Whereas the river water, we calculated end member values of around 1700 for both TA and DIC utilizing those salinity regression relationships. Incoming Gulf of Mexico seawater, again, has higher alkalinity and DIC than river water and is generally centered around 2100 to 2400 for the incoming regions in the Gulf of Mexico. Using these three end member values that we've calculated, we can then create a mixing envelope between our total alkalinity and dissolved inorganic carbon data. So here on the right, we have that plot of TA on the y-axis and DIC on the x-axis, with the three end member values that I presented in the previous slide plotted here. The rainwater at about 0, river at about 1700 for both, and seawater at a value of about greater than 21 to 2400. These points are then connected by lines to create a mixing envelope similar to water mass calculations, and the gray shaded region behind indicates the relative uncertainty and/or seasonal and annual variability in some of these values. Points that lie within the mixing envelope are potentially more influenced or heavily influenced by physical mixing processes and changes in the contributions for each end member value. When we plot our Galveston Bay data in this system, we can see the majority of these points lie within that mixing envelope, indicating that large-scale changes in the carbonate system are driven by mixing processes, particularly in the changes between river and seawater contributions. In particular, most of our data seems to appear between the river and seawater end members, which is indicative of that generally two primary end member system. However, our tropical cyclone data after Harvey, indicated by yellow here, show a much larger dilution effect with both lowered TA and DIC. When we compare this to our non-Harvey seasonal September 2018, we confirm that this dilution effect is most likely in response to the tropical cyclone, given that it is not a seasonal impact seen in other September sampling time points. We then applied an overlay of the aragonite saturation state calculated for each time point to investigate the potential drivers in changes in the carbonate system, where the saturation state color is indicated here with dark blue colors showing saturated values or greater than 1, and dark red colors indicating undersaturated waters or less than 1. And what we can see is that the majority of these undersaturated values are occurring in that September post-Harvey sampling time point and lie closely along the rain-river mixing line, indicating that rainfall and runoff is most likely driving a large portion of this undersaturation. In addition to investigating the potential influences on the mixing, we also utilize the three end member model to calculate the water column composition and potential influence that tropical cyclone had on the bay composition as a whole. So this plot, I'm going to show you two versions of this plot. The first is under pre-Harvey conditions, where we have water column percent composition along the y-axis, and the amount of rainwater indicated by the teal bars, the amount of river water indicated by the brown bars, and the amount of Gulf of Mexico seawater indicated by the dark blue bars. The plots are oriented so that stations closest to the mouth of the bay are shown on the left-hand side, and stations closest to the upper bay or near those freshwater sources are on the right-hand side. One of the things that we can see across this point before Harvey occurred is that we generally see increasing freshwater fractions of river water moving from the mouth of the bay to those freshwater sources and decreasing contributions of Gulf of Mexico seawater, as you might expect as we move away from incoming seawater and towards those river water sources. After Hurricane Harvey, now shown on the right-hand side with the same plots showing water column composition and rainwater indicated by those teal bars, we see a significant increase in rainwater after Harvey. However, in addition, we also see a dramatic decrease in the amount of seawater contributing for each station here. So generally speaking, we see very similar amounts of river water, but much lower amounts of seawater and much higher amounts of rainwater, indicating a displacement of this seawater in the bay with more acidic river water, essentially that hydraulic flushing mechanism that I mentioned previously. So what did all these changes result in terms of bay water chemistry? These are two plots showing pH on the top on the y-axis, as well as saturation state with respect to aragonite on the bottom plot here across June 2017 through September 2018, with this orange bar marking the occurrence of Hurricane Harvey and the high rainfall period. And what we can see is that following Hurricane Harvey, we have evidence for acidification or decreased pH, as well as decreased saturation state to undersaturated conditions after the storm. Most notably as well, the undersaturated conditions persisted not only after our 2-week sampling time point, but also after our 3-week sampling time point in September 2017. This study is the first documented record of undersaturation induced by a tropical cyclone, and thus represents a really important critical component, as previous studies had hypothesized undersaturation following a tropical cyclone event would likely not occur until end of century conditions. 2 months after the storm in November 2017, however, saturation states as well as pH appeared relatively to recover to those non-storm averages or pre-storm averages in June 2017 and the following months, indicating a recovery of the carbonate system likely occurred at some point between 3 weeks and 2 months after the storm. So if this is the first record of undersaturation following a tropical cyclone, why was this response so incredibly severe? There are 2 factors that we have hypothesized extended both the duration and the severity of the response. The first, the significant amount of rainfall that fell in the Houston region in particular led to significant inland flooding. In order to help mitigate some of the flooding, the U.S. Army Corps of Engineers enacted a controlled release of floodwaters from some of the major reservoirs in the region, marked by the Barker Reservoir here and the Addicks Reservoir here, northwest of the Bay ecosystem. This floodwater release into the Buffalo Bayou and surrounding watershed areas directly led into the Galveston Bay region, leading to increased inputs and prolonged inputs of this more acidic freshwater. These extended freshwater releases continued for more than a month after the storm, essentially extending the potential effect and influence of Hurricane Harvey stormwaters on the bay water chemistry. So this extended floodwater release likely prolonged this post-Harvey acidification response in the bay ecosystem. In addition, Galveston Bay is what we call a semi-enclosed estuarine ecosystem, meaning that it has very limited exchange with the Gulf of Mexico seawater to its southeast corner. This essential geometry of the bay can, in a way, exacerbate or enhance the effects of flooding on the carbonate system, given the fact that much of this water essentially remains in the bay for longer periods of time. So the combination of the extended floodwater release, as well as the limited ocean exchange and the relatively shallow depth as well of the bay ecosystem, led to an increased severity and duration of the acidification response following tropical storm or Hurricane Harvey compared to other studies that have investigated the potential influence of these storms on the carbonate system. In addition, our study represents the first documented point of undersaturation following a tropical cyclone. However, it seems relatively unlikely that this is the first ever in existence. In order to sort of provide a somewhat investigation into potential opportunities or potential occurrences where this may have happened in the past, we investigated the 10 wettest tropical cyclones shown on the right-hand figure here, comparing their percent maximum rainfall to Hurricane Harvey, indicated by the teal bars, as well as the comparison of a nearby bay ecosystem that could have been impacted and the total volume of that body of water compared to Galveston Bay, shown by the purple bars. While maximum rainfall rates tend to be relatively high compared to Harvey when we look at these tropical storms across the board, most of the bays are actually significantly smaller in volume than Galveston Bay. Therefore, it is possible that some of the responses we've seen in Galveston Bay may be similar or even more significant in some of these smaller bay ecosystems that have been impacted by high rainfall tropical cyclone events. The reason we don't have this record, though, however, is that tropical cyclones are a relatively unpredictable nature, and in order to investigate the response in water chemistry, long-term monitoring across these systems is necessary to understand changes and recovery after events like this. I also want to point out that some of these significantly larger bars here that are equal to 100% are actually because they are impacting the Galveston Bay ecosystem as well. So they're the same size bay, but slightly lower water percentages and may have had a potentially reduced or similar magnitude of effect in the bay ecosystem. The reason why this is such a cause for concern as well is that tropical cyclones are only projected to essentially increase in the amount of rainfall. This figure on the right-hand side shows projections for many different factors of tropical cyclones under future climate change conditions. These plots are present for each area of the ocean and include things such as tropical cyclone frequency changes or the intensity. But what I want you to focus on specifically are the red bars on each plot that indicate the percent change in the rainfall rates for these storms. The black line on each of these plots indicates the 0 line or mark of no change. And you can see that all of the red bars across the globe indicate increasing rainfall rates with tropical cyclones as climate change continues. And on a global scale, we see the increase in rainfall rates is approximately 15 to 20 or 10 to 20% higher than it is currently as those conditions and climate continues to warm. Therefore, high rainfall tropical cyclones may represent not only a current threat, but an increasing threat to many calcifying ecosystems, given their potential impact on the carbonate system in these environments. So to summarize the points that I have made in this paper, Hurricane Harvey caused a significant acidification response in Galveston Bay that decreased not only pH, but also the saturation state with respect to aragonite, leading to entirely undersaturated waters across the bay for more than 3 weeks. This acidification response is primarily in response to the hydraulic flushing that replaced seawater with naturally more acidic freshwater or rainwater in the bay ecosystem. In addition, the restricted exchange of estuary ecosystems may make these regions more susceptible to flooding and storm-induced acidification, meriting continued investigation and studies of this type of event in the future. While we present here the first recorded hurricane-induced undersaturation, it is likely not the first or only occurrence, marking the fact that while these stochastic or random point events may enact a future stressor, they are already potentially occurring today. Increasing frequency of high rainfall tropical cyclones under climate change may thus represent a significant threat to the coastal reef ecosystems around the world and a potential impact on the carbonate system and ocean and coastal acidification process. And with that, I'd just like to thank all the funding sources that supported this bay, as well as the wonderful team of scientists at Texas A&M who participated in a number of these cruise efforts and sample collection. And I'm happy to take any questions.
Thank you so much, Tacey. That was really interesting. That was fantastic. Yeah, if anybody, oh, I see a couple hands already. Oh, I see applauding. That's awesome. Does anybody have any questions? Feel free to raise your hand, or you can ask a question in the chat box. I'm on the lookout. Kim, yes, you have your hand up.
Hi, Tacey. Thanks so much. This is an outstanding piece of work, and this was an excellent presentation. We really appreciated you doing this. And I always have questions. This might actually be more of a discussion. So I'm gathering from all this that this, like saturation state event of below 1, which is incredible saturation state. That's sort of an end-member severe condition, I would define that as, right?
Yes.
And one of the things I know we're working on in Tampa Bay is how do we actually define a short-term acidification event in Tampa Bay? And I know that you guys are probably thinking about that for Galveston Bay as well. And so there's, to my knowledge, there's no right answer yet for any given estuary. And so what are your thoughts on, do we define these short-term events based on sort of ecological tolerances like oyster growth saturation states of 1.9 or deviations from non-storm seasonal means? How are you guys thinking about that for Galveston Bay?
That is a great question. I actually don't know that I've thought in terms about like how we would define these short-term events, because I know often on the West Coast, right, you're seeing short-term events from upwelling and other things that are a little bit more predictable, for instance. I think that it's probably a good metric at least to compare to long-term averages. However, declining long-term averages may also influence how severe a response may actually end up being, which could impact your sort of factor. But I also think it's important to incorporate some of the ecological factors, because I know, for instance, coral sort of have the ability to potentially persist or calcify under low saturation conditions because they upregulate their calcifying fluid. It's not a complete fix, but it may potentially help some resistance or ability to tolerate occurrences of these low saturation states, whereas oysters, for instance, don't have that same biological capability, and so they may be more susceptible to shorter durations of really low saturation state than maybe corals or other calcifying organisms. So I think it's probably almost like a mix of these two factors that you've pointed out, right? The ecological indicators of at what point are you seeing poor conditions or responses, and at what point or how far away from your long-term average is this change occurring? Does that kind of answer your question? I don't know that we've decided on a term exactly for Galveston Bay or a period, but I think that at least from the storm event, the multi-week prolonged conditions is kind of the point of concern.
Yeah, actually, that's super helpful. And like I said, there's just no right answer at this point, and we're dabbling with the same issue in Tampa Bay on, duration, magnitude relative to seasonal mean versus an annual mean. And so, always happy to see these pieces of work come out and have these discussions. And I'll probably pick your brain on this some more as we try to define this ourselves. Yeah.
And I think, coastal environments are also really hard because the seasonal mean is so hard to determine because they have so many things impacting that, right? Like you might have a year where you're under severe drought for most of the year, or a year where you're under continual flooding. We just had a year or a couple of years ago in 2019 where there was just so much fresh water in the bay. Your seasonal mean is a little wonky for that year, right? So I feel like it's definitely a complicated process. The time of question and all that.
Yeah. And then based on, was it a rainfall event or was it a HAB event with a fish kill and remineralization of dead organics? I mean, it's like a lot of stuff there. So
yes,
that's fantastic. Definitely. And I actually had one other short question, and I might have just missed it. Yeah. We were showing the percent water column composition graphs. Did you develop those based on discharge and rainfall volume estimates? I might have missed that.
So I actually did this based on the chemical analysis. So I utilized alkalinity as a conservative tracer and essentially did a linear equation calculation utilizing those estimates from our freshwater end members here, and calculated essentially if I have this TA in my sample using salinity and alkalinity and the fraction amount, and I have these three end members, what's the most likely combination of those three pieces that creates or recreates these chemical conditions? So similar to what you would do essentially for a TS, like a temperature salinity mixing of water masses in the open ocean, I utilized alkalinity here as a tracer, given the fact that most of the influence or change in the alkalinity system for Galveston in this study is driven by physical mixing and not biological impacts.
Great. That's super helpful. Thank you so much.
Of course.
Thanks, Kim. How about another question for Tacey? Anybody else? Angelos.
Hi, can you hear me?
Yes.
Yeah.
Oh, awesome. I've been trying to activate it for like 30 seconds already, the microphone. This is a great presentation. I really appreciate it. I look forward to rereading your paper as well. I really appreciated actually seeing those salinity to total alkalinity plots because, those are kind of very telling, and people that don't work in the open ocean often hesitate to show them because they show a mixed bag, right? So
Hmm.
I wanted to actually pose to you, Tacey, from your experience, a question. If you have a suggestion, where, as in our case here in the northern part of South Carolina, where we don't have this clear kind of input, a freshwater end member like a river, but we do have these intermediate waters in marshes. We have the conundrum of what can we use as a freshwater end member, and typically it's runoff, so it doesn't help us very much. And I was wondering whether you had any reaction to that. You can suggest guidance to us because it's a very difficult problem to resolve.
That is a very valid question, and I know that it is harder when you don't have those clear sort of river end members. And even in this study, I'm assuming a lot of things, right? Like this is essentially a combination of groundwater and potential
Right?
marshland input and river water systems. And I've compared it as well. We have some limited samples collected from the freshwater, like near the mouth of the freshwater rivers in the actual rivers themselves. And they do tend to agree in terms of the relative contribution of each river run member and the values and what that looks like compared to my
Wow.
estimated value. I think that essentially if you can't get sampling right, you need some sort of conservative tracer to make that estimate, and that's not always the case for coastal ecosystems, so it definitely makes it a lot harder.
Yeah,
Galveston is really unique in that the TA and the DIC show relatively consistent linear trends between salinity, which is
absolutely. Yeah,
another sort of like, that more support for physical mixing being our dominating process.
yeah,
And preliminary data also sort of shows that a lot of our biological data may not be as heavily correlated with the carbonate chemistry. So it allows us to essentially utilize that to estimate a freshwater end member without needing or having the specific
right.
sample. But
Yeah,
I recognize that in a coastal environment, that's not always the case because there are
yeah,
definitely areas where you see significant drawdown or calcification, for instance, in like large reef flats where the water has high
right.
residence times and can't really project that way. But I'm not exactly sure the best way to go about it for a marsh system, for instance.
But your reflection is pretty useful. It's
Yeah,
good to get reassurance from people
yeah,
that think about this a lot longer. Yeah.
and
Um, Go
I would
ahead.
say too that I think utilizing all those sort of plots in tandem gives you a lot of nice background and verifies whether you can or cannot use them as conservative tracers
Oh,
for your region, right? So adding in those plots of biomass in comparison to carbon dioxide levels or DIC and pH, and then
right.
utilizing the like salinity extrapolations. But I definitely think it's a little bit more unique. I know alkalinity tends to be more conservative than DIC and MONI systems, but
Yeah.
having that sort of production helps a lot.
Yeah, that's fascinating. I was very very surprised, pleasantly, at the linearity of the relationships you showed when seen, in these sampling events that you had. And I
Mm-hmm.
do understand that November data, those yellow triangles, when projected, they actually they show an elevated anticipated alkalinity at a
Mm-hmm.
salinity of 35. But does it uh, I the data, that's just the linear projection within that sampling event you had. uh,
Right.
so I
Yeah.
I was wondering if you had any idea if that's say a statistical artifact, or you know it does reflect oceanic end member alkalinity that was slightly higher at that point.
Yeah.
Because it's not really outside what would be unusual.
Yeah, it's not entirely outside what would be unusual. I don't think we do have some sampling in the Gulf of Mexico, which I don't have a slide for it right now, that corresponded with at least the 2017 data for June, September, and November. And the alkalinity wasn't quite so high as the linear projection is sort of anticipating. But they all sort of remained around the same time, right? A lot of the alkalinity in the Gulf of Mexico, especially in that coastal region, is driven by Mississippi River inputs. And
Got it.
that river essentially has a high input in the spring and summer, so most likely your fall is not going to have the same
Got it.
high alkalinity input. But even when we incorporated the Gulf of Mexico data into these lines, the November still had that sort of depressed freshwater end member. And we think that could be, if it is not a hurricane response, like a recovery response, then it could just be variability in which river end member is contributing the primary amount of freshwater to the ecosystem. Because you have the Trinity, which is normally about 50 to 80% of the freshwater, but there's also that Houston shipping channel area, and they generally drain very different deposits. One is more limestone, one has carbonate minerals, and so you get varying chemistry, which is likely controlling some of the seasonal
Interesting.
variability.
Yeah. I was
Yeah.
wondering, there's these freshwater parts, in some of your dates, some of your months, they're actually quite high, but it would be explained this.
Yeah,
Carbon, limestone.
our some of our preliminary data in the river end members, like the Trinity, had TA and DIC both in the range of 2000, which is more like what you would expect for seawater or, for instance, like the Mississippi. So I think that that's just sort of
Sure.
driven by when you're seeing the most freshwater input from the Trinity versus other river sources in the region. And I think that's part of the variability. So that's why we utilize an average end member for our mixing plots and calculations and things instead of a specific
Yeah,
month, because we don't have enough data from the specific rivers to
sure.
sort of attribute each time period.
Excellent. Hey, thank you very much. I really appreciate it.
Yeah, of course.
Thanks, Angelos. Anybody else? Okay. Well, in the chat box, if you do have a question you'd like to ask Tacey directly via email, I left my email there. Reach out to me and I'd be happy to connect you with Tacey to continue the conversation. And with that, Tacey, I really want to give you a big thank you. It was a fantastic presentation. You're going to do great. Great at and we're all supporting you. So please stay in touch and let us know what's going on. And yeah, hopefully we'll see you on some GCAN calls in the future.
Yeah. Thank you very much for having me. I appreciate it.
Absolutely. Thank you so much. And thank you everybody for taking the time to join us.